And welcome back to another episode. So this is going to be the fourth video of the General Relativity series. Today I've decided to just really stop explaining kind of low-level topics and really just dive into some of the more, I guess you could call meat and potatoes of the theory. So today I'm going to be using this website. So it's called Einstein Relatively Easy. There's a bunch of people that are nerds out there that are very interested in kind of detailing all of the mathematics behind this. So just to kind of recap, what is the main thing about general relativity? So the main thing about general relativity that makes it very difficult compared to other theories is essentially the fact that in general relativity, you have a few more ingredients that kind of constrain your problem. One being that the speed of light is what is called an invariant, meaning no matter where you are, so I could be out floating in the middle of the universe, I could be on a submarine, I could be at the top of a very tall skyscraper. If I'm able to, let's say, if I want to measure the speed of light, essentially the idea is that we should all measure the speed of light to be the same thing, meaning in some kind of weird way, there's like this global property or universal property of light that it's the fastest speed that there could possibly be. The second thing about general relativity is that we learn about the fact that matter and matter curves space, and in general relativity, space-time is kind of this weird thing, but essentially what you do when you talk about general relativity is you have an underlying kind of thing called a manifold. So the manifold is it's a shape. It's a four-dimensional shape, but it's a shape. And essentially the manifold has a lot of very nice properties. So if you took any calculus, manifolds are able to be, you can take a derivative of a manifold. And a manifold, again, it's represented by a four-dimensional vector, essentially. But the manifold, you should be able to do a lot of the things that you're already familiar with. So we need to be able to differentiate it. Some few other properties that are not as important to discuss, but essentially you can think of it as a shape. So a good example of a manifold is a sphere. So for example, a soccer ball or a basketball, those are what we call manifolds. And in mathematics, I know it's a very weird term, but essentially the idea is that most nice shapes that you could deal with in math, that you could differentiate things with, these are what we want to restrict our attention to in general relativity, for the purposes of the fact that any kind of physics theory requires a lot of derivatives. So if you need to take derivatives of things, you can't assume that you can't have the assumption that, the thing we need to be looking at can be differentiated. Like, of course it has to be. So you make this requirement, and then you give it a name. So they called it a manifold. So essentially here, though, I'm just going to kind of go down. So there's this thing called, it's called the Einstein field equations. So the Einstein field equations are what general relativity is. And what I mean by that is, the Einstein field equations give you the relationship between matter and curvature. So there are a lot of complicated concepts involved in the equations themselves, but the main idea of the equations is that the solutions to them tell you how space can look based on how much matter is in there. And when we say matter, usually general relativity deals with very large scale. So you and I are very negligible in terms of any kind of gravitational field we may have or anything like that. But if we're talking about the sun, or we're talking about Venus, or we're talking about these very massive bodies, then general relativity becomes very important to use. So it's really at those kind of time scales we need to think about matter and what matter is, and kind of how it relates to curvature. And mainly, when you think about curvature, I think intuitively you might think about how an object, like if it's flat, for example. So like the walls in your room, for example, they don't have any curvature. So they're not moving, like they're just totally flat. But let's say you had like a bed or something that had it was kind of like a ramp, like it looked like in a ramp shape or something, like that would have curvature, for example. So curvature, I think, hopefully is an intuitive idea, but essentially curvature is the important thing to be discussing in the context of general relativity. So yes, okay. So how is general relativity done in practice? So what you want to do is you want to first identify the shape of space, because the weird thing about general relativity is that you actually assume what the underlying shape is that you're on. So, and maybe this might be hard to get across, but essentially there's a difference in geometry between an intrinsic versus extrinsic treatment of an object. So we can talk about doing geometry from, let's say, like outside the object. So let's say, for example, I could talk about doing geometry on the Earth, except I'm actually in the space station and I'm doing geometry from there. Or I can talk about being on the Earth and doing geometry of the Earth on the Earth. So like I'm measuring things on the Earth, specifically on the Earth's surface. Like let's imagine there's no houses or anything or any buildings on the Earth, and it's just like the forest and whatever. And I'm doing like with my ruler, I'm measuring stuff on the ground, and I'm doing stuff like that. Like that would be called an intrinsic thing. So in general relativity, we're always dealing with intrinsic properties of the underlying shapes. So this is why people ask, like, oh, what is the shape of the universe? Those kinds of things, because in general relativity, we want to look at the intrinsic properties of the universe. We can't talk about the universe from like outside of the universe. We don't know if that's even possible. So you want to talk about the intrinsic shape of the universe, because that's what's interesting in general relativity. Because what we can do is, based on how the planets and everything are spaced out, that tells us something about how our underlying shape looks. It's very weird stuff, but anyway, let's continue here. So what I want to talk about today is this thing called the Einstein-Hilbert Action. So what is an action? So in physics, this word action comes up a lot, and it's not that terrifying. It's actually something that is very helpful, and it's a different way of looking at what you're trying to do in physics. So an action is something that physicists use to derive equations. And what I mean by this is the action essentially will operate on something, meaning the action will do something to some object. And then based on that action, you should be able to figure out some kind of relationship about the quantity that you're looking at. So specifically in physics, there's this concept of a Lagrangian. So I'm not going to use that fancy term, but essentially what a Lagrangian is it's some kind of physical law where you're looking at, like, let's say like the motion of a ball through the air or something. Now you can have some kind of what are called differential equation about this, which is essentially telling us how it moves in time, generally speaking. Physics, it's all about stuff moving in time for the most part. So the Lagrangian is telling us how when this object is flying in the air, it's going to tell us something about how the energy changes of the object, like kinetic versus potential energy. It's going to tell us some things about that. And so what's actually important about this, not so much what a Lagrangian is, what's more important about this is that in nature, it seems to be the case that in nature, whatever this Lagrangian is, which is essentially describing a physical system, like throwing a ball, this Lagrangian will always minimize itself, meaning nature is always picking the most optimal path to move over time. And so this is really nice because in mathematics, a lot of things are very easy to optimize using derivatives. So, and you don't need to think about that much, but the main idea here is that if we can find a Lagrangian to minimize, then we should essentially be able to figure out what the equation describing the physics of our system is. This is the main idea. So essentially, what kind of happens is you can approach physics from many different points of views, actually. There's many ways to get the math out of physics. There's another way called the Hamiltonian method. There's the Lagrangian method, and then there's Newton's method. So these are actually all equivalent methods, but some are easier to use in certain situations, and I won't explain why, but preferably we want to use Lagrangians. They're a lot easier to deal with. So going back, so in the development of general relativity, so the theory was actually finalized in 1915, and nobody really paid much attention to it for many years. It really picked up traction as cosmology became a big thing. People started becoming interested in black holes and these kinds of things. So general relativity at the time, special relativity was more important, I think. Special relativity is kind of, special relativity is a subset of general relativity, except special relativity doesn't include any curvature. So we talk about it as all of the underlying shapes, those manifolds I talked about. These are all what we call Euclidean manifolds. And what does that mean? So it's really like our universe. So everything is flat, meaning nothing curves at all. So none of the shapes that we can deal with curve at all. So they have to be a flat. So that's obviously not what happens in real life. So we have to. So Einstein had to figure out a way of accounting for things like acceleration and for how curvature operates with gravity. So anyway, so what is this? So this is, to be honest, it's quite advanced math, but I want to try and explain it because I think it's more important to look at what the more difficult parts of the theory are, because it is a difficult theory. So, okay, what are we doing here? So you see this, and if you took first year university, maybe you know what this is, but what you should think about when you think about integral signs is you're just adding up a bunch of things. Okay, so what is this? So you see this d to the 4 of v. So d to the 4 of v, what this is saying is this is really the volume. So in math, they found a way to say, well, in 3 dimensions, we know what volume is. You know, like if I have a cup, I can think about how much volume that cup is. If I have a container of any kind, you know, it's got some kind of volume to it. So what you can think about is, well, is there a way of bringing that idea of volume into higher dimensions? Because that's what math is about. It's about generalizing. So they figured out a way of doing it. So you can talk about volumes of 4-dimensional objects. You can talk about them of n-dimensional objects. It's actually quite simple. You think about how you do volume usually. So if it's like a shape that we know very well, like a circle or something, you can easily think about like, well, we could figure out the volume of a sphere. What about 4 dimensions? Like you carry out the same kind of operations. So with like a 4-dimensional cube, so a cube is defined as like all the sides are the exact same length. So it's actually very easy to think about what a 4-dimensional volume would be. You literally just do the exact same calculation you did before. So you would just take it to the 4 instead of to the 3. So, you know, if all the sides are are length 2, then the volume of a 4-dimensional cube would be 2 to the 4, which in this case would be 16. So 16 units. That's how big the volume would be. Essentially, though, what we're saying here is, for this Lagrangian, d to the 4 is really saying whatever our shape is underlying that we want to sum over, we're going to say how does the volume of the shape change as we cycle through all of the points that we have in our space on our manifold. So how is this volume changing over time? That's what's important here. And then the Lagrangian is it's kind of like keeping track of what the state of the system is at that point. And then what we want to do is we want to sum over all of these things. So the reason we want to sum over all of these things is because if we can sum over all of these things, we want to try and find a way of determining what is the particular, how can we always figure out what minimizes this value? We want to minimize what this sum is. So we're adding up, like let's say we're adding up 100 things, okay? So we have 100 things, and then what we're going to do for each of these 100 things, we're going to evaluate at every point, one of these 100 points, we're going to evaluate this Lagrangian. So like, let's say the first value gives us like 5.4 or something like this. And then the volume of that at that time period for the first one is like, let's say 10. So now we have 50, it's 5.4 times 10. So it's going to be 54, whatever the units you might be working in. So anyway, and then we do this for the second one, and then we do it for the third, and then we keep doing it for all 100. We add up all these numbers, and then we get some number at the end. Let's say the number is 1,000. So we get that our action is equal to 1,000. Okay, now what if we do it for 1,000 points in time? So what we're going to do now is we're going to identify 1,000 points, and then we're going to calculate this number, and then we're going to add them all up. We're going to do it 1,000 times. What if we do it 1,000,000 times? What if we do 100 million times? Okay. This integral is just saying, what if we add up an infinite number of things? What can happen? So, yes, so here you see that this D4 is the volume element, so it's the 4 volume element. Now, the volumes of shapes that aren't like cubes or rectangles or stuff that like are easily identified, they are a bit more complicated, but we don't need to worry about that. You just need to know that you can find the volume of it. That's what's important. Okay. So yeah, so the volume, the volume element, Yeah, so you see here, so there's some weird stuff they do in relativity. They have some weird coordinates, but essentially you should think about this as like, this is the first number that your vector is. This is the second number, third number, fourth number. It's not that important. And then you see here, some Jacobian. So you don't need to worry about this too much. You can just think about this as like, for different people, like how do we translate like how different people see the world? This is kind of no worries about this. Don't need to worry about this. Don't need to worry about this. Don't need to worry about this. Yeah, see, what you should know is down here. Yeah, this is what's important. Okay. Down here. This is important. Okay. So what we have here is what we're going to do is, I know I talked about the manifolds a bit earlier. What we want to do is we want to take a volume. We want to take an integral over that shape that we have. So we're going to first identify a shape. And then the second thing we're going to do is we have to integrate this quantity. Now, what does this actually mean? Okay. So this G here is something that's called the metric tensor. And it's actually not that scary, but what it does for us is it gives us a way to measure things. So if we didn't have this G here, we wouldn't be able to like measure these points in time and how they relate to each other. So the 100 points I talked about, we need this metric tensor to like kind of make them all the same. So we can talk about like the distances between each of them being the same. Kind of think about this in the same way that like, when you want to talk about like gallons of water versus liters of water, you need a kind of some way of equaling everything. So in order to do that in general relativity, to make all the distances kind of equivalent, we need to talk about this metric tensor. So that's why this G appears. You don't need to worry about taking a square root of it. It's not a big deal. But it's essentially, this is going to be our volume. So this is going to keep track of our volume, this element right here. The R is it's called the Ricci scalar, but all we need to worry about is that this thing is it's just a bunch of derivatives. So there's nothing really important going on here. Now, be aware that this is a very complicated integral actually to generally do. And you can see here there's a remark. So it says this integral is taken over the whole of space-time if it converges, and if not, S can still be made so by integrating over an arbitrary large. Okay, so what this is saying is essentially if the shape we chose is a really bad shape, so in the sense that like when we start calculating these numbers, if we're starting to see that like, oh no, like we're getting infinity like all over the place when we do our summing, that's really bad. We don't want that. So what we can do is, instead of taking it over our entire shape, so like let's say our shape was like a line, it was an infinitely long line, so from positive to negative infinity, all the numbers there. Okay, so let's say when we take up our sums, like when we start adding up our values there, we get a bunch of numbers and they're just blowing up. And the more we add on, the more it's blowing up, and it just doesn't stop. The problem with this is that like we can't deal with infinities. So what you want to do is, instead of looking at the entire line, you can just look at like an arbitrarily big part of it. So like, let's say you look at the numbers, instead of like infinity to minus infinity, you might look at it from like 50 to minus 1,027,000, something like this. So this is what this is saying, is just like, if you're adding stuff up over the whole underlying space and it's like blowing up, that's not good. So what we want to do is we'll just calculate our numbers and our derivatives and whatnot on a smaller region that doesn't blow up. So we can do that. That's usually pretty good. Okay. So this is how, what I should explain again. So the Einstein field equation is the most important part of the theory. It actually encapsulates everything you need to know about general relativity. And its main purpose is telling us different shapes that the universe can take on, given the fact that it has our specific physical laws. So for example, like F equals ma, Newton's second law, is actually something that can come out of the Einstein equation. So it tells us like all of the physical laws that relate to gravity, this equation. Okay, so what's going to happen here? So what happens here? Okay, what I want you to think about in terms of this, we're not actually going to go through this, but what you should think about what they're doing here is that we have this action. So what you should think about is that the action will operate on something. So maybe the simplest example is like, think about really hard, try and visualize in your mind like throwing a ball. So imagine you throw this ball, and then what you want to think about is, imagine like some ghost came by and started to maybe tap your ball slightly, and maybe now it's possible that your ball could take like any different path it wants. So like this person just can like smoothly like play with like move the ball up and down, like it can imagine like it's like got a controller and it's like controlling the ball that you threw. Okay, so the idea here is we want to apply this action. We want to apply it to something that's like a real physical thing that we can see in our world and like measure and that kind of thing. So the idea would be that like we want to see all of the different paths that this ball can take from me to the wall. And what we want to do is we want to talk about, based on all these different paths that the ball can take, we want to pick out the one that minimizes how much time this ball is spending in the air. Because what we realized is that, nature always likes to optimize things. So if nature likes to do that, then that's the best way to figure out what nature is actually doing, by figuring out how it's optimizing something. Okay, so what's happening here is there's something called the principle of least action. And this is essentially the idea that like nature is constantly trying to optimize what it does. The second piece that you should notice here is there's this weird delta logo. So delta of the action is equal to 0. What this is saying is that nature is going to optimize itself when the path that we choose to act on is equal to 0, meaning that we don't deviate at all from what nature's choosing, meaning there's no difference between nature's choice and our choice. That's what the choice that we want to pick out is. Okay, I think that hopefully makes sense. It's the same way of thinking about like, if we're trying to figure out like any of the, like if you took first year physics, if you want to try and figure out like how a ball travels through the air, what you might be able to do is, well, what if I can say like, what if the ball travels like through a bunch of points, and I can assess like how all of these different trajectories that the ball took that are possible, how these line up to reality, and then I can just figure out like, well, nature's always optimizing, like it doesn't want to use that much energy when it's and so like because of this principle, I can always find the most optimal result. Anyway, I don't know if that was helpful, but yeah, so here, this math is quite complicated. Maybe I'll describe a bit what's happening here. So the symbols are more what I think are complicated, but what's actually going on is not that complicated. So what you want to do is all of this this action, so we don't want to actually calculate it right now. What we want to do is we want to take a derivative of it. So this little delta here is just derivatives. Don't think about it any further than that. And what we can do is we can bring it inside. Okay, so we'll bring it inside. So you see that this person has written these weird symbols in here. essentially what this is a matrix. So this is some kind of matrix that has a lot of like at every different like point in the matrix, there's a lot of different derivatives going on. Very complicated. Don't worry about it. And then what they're going to do is they're going to apply what's called the product rule to this. So when you take like derivatives of functions, you learn about like, oh, there's this product rule, there's this and that. So like, for example, the derivative of x multiplied by e to the x, you'd have to do the product rule because you have two functions that both depend on x, but they're not, you can't write them in, essentially you can't write them as one singular function. Like they're both going to vary differently. So what you do is, you take the product rule. So you're using the product rule here to this quantity here, and you get some terms out. So you see that this derivative terms, they're still getting carried over. And then essentially, so they're just working out some steps. It's pretty complicated, so don't worry about that. But I just want to show like what the actual math of this looks like. And again, what we're trying to do is we're trying to figure out how, essentially in some weird way, how nature would choose us to move in space-time. That's kind of the idea here. We're trying to choose how we would move in space-time. So you do some more steps, complicated stuff, more complicated stuff. Here what they're showing is we have a term here. So this thing right here. So you see right here, this term. They calculate this thing in another article, but we don't need to do that. It's equal to this. Now what you should know about this is that this is a sum. So what they do in physics, they don't write like the sum sign. They don't tell you that they're adding stuff up here. But essentially what they're doing is there's this mu and v, and then the mu and v up here. These are actually coordinates. So each of these values will tell you like elements of the matrix. So these values go from 0 to 3 because that's what they do in physics. But essentially it's you're going to have 16 values here that they're adding up. So think about this as like a sum over 16 things. And then each of these values will tell you like what element you're at. So for example, like the element 1, 1. So this would be g of 1, 1 delta g of 1, 1. And then that would be some element. And then you go to the next one. Maybe you do g of 1, 2. And then this one would be g of 1, 2 as well. So you're just going to keep doing this until you reach the element 4, 4, 4, 4. Anyway, not important. They figured this out in another article. Next, you move some other steps. Now, maybe I'll explain why are they doing what they're doing here. So why are they taking the derivative here? Why are they doing all this? What you're trying to figure out at the end is you want to see if like anything cancels out. And primarily what you want to do is you want to try and figure out some kind of condition that you can impose that says, if this thing is always like this, then I know that this action, the action we describe, is always 0. That's the main goal. You want to figure out, at all times, I want to know if I plug in something that satisfies this relationship and I plug it into my action, then it's always going to be minimizing the action. I want to know that. Because if it tells me it's minimizing the action, then I know that's what the experimental results will be, for example. So for example, if you want to measure light going around the sun, you're going to need a way of figuring out what the predicted value is to confirm it. So the only way this would happen is you need to know what path the light would take around the sun, which in this case will always be satisfying the Einstein field equations because nature always chooses the most optimal path to go through anything. So in order to find out an experimental result, you actually have to do this kind of stuff to figure out what light would actually do under this action. Anyway, so you see here, they get down here, so they have some integrals, some weird signs. Just think about this as like they're going to be summing up a bunch of things. So just think about a ton of things being added up right now. And what's going to happen here is they get it to this point. It turns out that this value here, this thing is just 0. So you don't need to worry about this. This is 0. And then they have this element here. Now, what you need to know about here is that the main condition you want to impose is that you want to say that, okay, well, if this thing is 0, if this thing is never 0, this thing's never 0, this thing's never 0, what you want to say is you want to figure out a way of saying, this thing I have in the brackets here, if this thing is 0, then that means the whole thing is 0. That's what you're essentially going for. And what it turns out is that yes. So it turns out that if this thing in the brackets here is 0, then no matter how many sums you do, the full thing's gonna be 0. So that's when. So what that would mean is, if you can figure out what this is, then you'll automatically know if you have something that satisfies this, which again I haven't really told you what it is. If it satisfies this, then that's going to be essentially what you should look for in experiments. That's how you'll be able to predict stuff. So anyway, I'll go down here. So we take this stuff in the brackets here. We're going to move it down here. Okay. So what we're going to say is this is 0. So what happens if this is 0? And again, what this is that this is called the Ricci scalar. And this is a 4x4 matrix. Both of these things, these R's. These are 4x4 matrices that have a lot of derivatives in them. So every single like cell you have, think of an Excel spreadsheet, like a 4x4 Excel spreadsheet. Every single cell has a bunch of derivatives going on. And essentially they're taking derivatives on like some 4-dimensional function. Not important, but essentially this is what's going on. So yeah, so then they show here that the second this thing is 0, not important. Yeah, some very complicated. What's going on here is some very complicated stuff, but this is essentially tensor geometry. Don't worry about it. These are all 4-dimensional things as well. Don't need to worry about it. Don't need to worry about this. Don't need to worry about this. It's very complicated. I just want to show because I think it's fun. Not important here either. Yeah, not important here, not important here, not important here. Yes, okay. So, yes, so we have this thing. So this is called the Einstein field equations. This is what they look like in a vacuum. So this is an area of space-time that has no matter at all and no energy at all. The reason we know this is because typically when we write the Einstein field equations, there's another 4x4 matrix on this side. But right now it's 0. It's just all 0. So it's not contributing anything. So this is the Einstein field equations. So what this means is that in a vacuum, which is something that you can create in empty space, that is something that you can do. What this tells us is we should know what the shape of space is in a vacuum, which is going to be flat. It's going to be flat. That's what comes out of this. Again, another complicated exercise, but what we figure out is that it's flat. So in spaces where there's no like large planets or anything like that, the shape that space actually has there is flat in some sense. Okay. This video is becoming very long, but I might as well just keep going. So let's say now that we want to actually include objects, like things that have mass. So what we need to do is we're going to add a term to this equation. And I'm not going to write this. I'm not going to write this out. Essentially, you're going to do the same thing you did before. You vary something, you do this, you do that, yada, yada, yada. And in the end, you get this equation. Okay. So this is the full Einstein field equation. What this is saying is this is a 4x4 matrix on this side. This is a 4x4 matrix, 4x4 matrix. What this is saying is that we have on the left-hand side, this is the manifold I talked about earlier. We're going to take some measurements of the curvature of the manifold. So we need to figure out a function that describes the curvature of this. And then what we want to do is we want to talk about how this curvature of this shape relates to the energy density. So essentially the idea is that like energy, you've heard of E equals mc squared. So there's a relationship between matter and energy. What this really means is that like whatever energy really is, whenever you have like matter, because matter is made of atoms and it has electrons on it and that kind of thing. All of us have energy. So there's like an equivalency between the matter we have in us and the energy that we have. And essentially what you do in general relativity is you look at how much matter energy density there is, meaning like a density is like some kind of a division going on, like how much matter divided by energy per per inch you have or something like that, some kind of unit of scale. Anyway, not important. All this equation is going to tell you is, if you can tell me some like underlying shape, we should be able to tell you how, when we move around this shape, how the distribution of matter around us changes over time. So think about like how like a galaxy moves across space. If you could tell me the shape that we're dealing with, the underlying shape that we're dealing with, I should be able to tell you over time how it's changing and how the matter energy is changing on it as well. Anyway, it's very complicated stuff. This is mainly just to be something that if you find interesting, like you can look, there's other links here. So there's, this is Leonard Susskind. He's a theoretical physicist at Stanford. If you want to look at kind of more of the theories behind it, it's very interesting. But anyway, that's the video for today. And maybe I'll do some other stuff later on. But anyway, thank you for tuning in. Bye-bye.